One of the most difficult challenges in classical mechanics is predicting the trajectory of a real extended object. A tumbling wrench is made of countless microscopic particles, all moving in slightly different directions at different speeds. To solve this, physics does not attempt to track every single atom. Instead, it identifies one specific mathematical coordinate that dictates the translational motion of the entire system. We call this coordinate the center of mass. It is the exact location where we mathematically pretend all the mass of the body is concentrated. Look at this diagram showing the simplest theoretical model: two identical point masses sitting on a one-dimensional x-axis. The center of mass is the single bright dot located between them. Because the two masses are equal, this balance point sits precisely at their geometric midpoint. Watch what happens if we make one of these masses heavier. The balance point immediately breaks symmetry and slides along the axis toward the larger mass. The center of mass is a dynamic mathematical coordinate determined by the distribution of mass, not just physical geometry. We calculate where that point lands using a specific formula. In the numerator, we multiply each particle's mass by its position coordinate and add them together. Finally, we divide that sum by the system's total mass. The result of this calculation is defined as the mass-weighted mean. This simple fractional logic is the universal algorithm for finding the exact balance point of any physical system. Physical matter does not exist on a flat one-dimensional line. We must expand this logic into a full three-dimensional coordinate system. This animation shows a system of n particles scattered in 3D space. The formula expands to use position vectors, tracking x, y, and z coordinates simultaneously. The sigma symbol tells us to sum up the mass and position vector for every particle. A real rigid body contains trillions of atoms. Calculating a discrete sum for every single atom is physically impossible. To make the math functional, we have to stop counting separated points and shift to measuring solid, continuous matter. We handle this by treating a tightly packed system of particles as a continuous mass distribution. As the particles pack into a solid block, the formula morphs. The discrete sum from the sigma symbol becomes a continuous integral. We multiply the position vector by infinitesimally small mass slices, labeling each microscopic slice dm. While this calculus provides an exact answer, running a full continuous integral for every object is highly inefficient. By identifying the physical symmetry of an object, we can frequently bypass the calculus entirely. This shortcut applies directly to homogeneous bodies. A homogeneous body is an object with a perfectly uniform mass density, meaning its mass is distributed evenly throughout its entire volume. This diagram shows a uniform thin rod centered on the origin. For every tiny mass element dm at position x, there is an exact mirror element of the same mass located at negative x. Because x and negative x sum to 0, they cancel each other out. The integral inherently places the center of mass exactly at the geometric center of the rod. This diagram shows a non-uniform two-dimensional shape, an equilateral triangle with 100-gram, 150-gram, and 200-gram masses at its vertices. The calculated center of mass lands closer to the 200-gram vertex, missing the geometric center. Compare that to a solid, uniform triangular plate. By drawing three medians from the vertices to the opposite midpoints, we locate the geometric centroid. The reflection symmetry along these medians dictates that the center of mass must lie exactly on their point of concurrence. This rule applies to homogeneous rings, to solid disks, and uniform spheres. Their center of mass will always align with their exact geometric center. For any homogeneous symmetric shape, the mass-weighted mean is simply the geometric centroid. How do we calculate the balance point for an asymmetrical rigid body like an L-shaped lamina? This 3 kilogram L-shaped plate can be geometrically divided into 3 1x1 meter squares. We treat each symmetric square as a single point mass at its geometric center. This leaves us with 3 1 kilogram points at coordinates 0.5, 0.5, 1.5, 0.5, and 0.5, 1.5. We simply apply the basic discrete mass-weighted mean formula to these 3 1 kilogram points. Any complex continuous body can be reduced to a simple system of point masses. The mass-weighted average of these 3 points lands at 5/6 of a meter on both the x and y axes. When we draw the L shape back in, you can see the center of mass sits perfectly in the empty space inside the elbow. The point representing the object's entire mass contains absolutely no physical matter. Mechanically, if you toss this object, it will rotate smoothly around an invisible pivot located in the empty air between its arms. Starting from a simple one-dimensional line, integrating continuous physical mass to find this invisible coordinate. The center of mass is the governing point for both translation and rotation. It is the absolute mathematical nexus of a system, the one coordinate that tells classical mechanics exactly where an object truly is.